Welcome. This video focuses on pointers and arrays and how they are related. So let's start with the concept known as pointer arithmetic. So imagine I start with a int variable x and a double variable y. I get x's address and get a pointer to it. So I store that as p1, a pointer to an integer, and I print out p1, and I get this hex address. Right? So what this represents is the memory address where x is actually located. And I can see it ends in EA4. That's the last three digits of the hex decimal number. And then I add 1 to that pointer, right, to this EA4, and print out P1 again, and I have EA8. And I added 1 and I went up by 4. Well, I do the same thing with a double. So y is a double, I get its address, I store that in P2, which is a pointer to double, I print it out, and I see that, okay, y is located at E98. Fair enough. I add 1 to P2, print it out again, and now I see that the address that P2 is pointing to is EA0, which is actually 8 bigger than the previous value. So adding 1 to my int pointer changed it by 4, adding 1 to my double pointer changed it by 8. What's happening here is what's known as pointer arithmetic. So when you add or subtract to a pointer, what you do is you change the memory address it's pointing to, but you do it in the kind of an increment size of whatever it's pointing to. All right, so if I've got an int pointer called p, and it's pointing to x, so we get x's address, and we have p point to it. So in memory, it might look something like this. Right? Here's x that starts at memory address 104. It's got the value 5. P is the pointer. It's storing x's location, so that 104. And now I go add 1 to p, to my pointer. Well, it would become 108. That would be the new address. Basically what the compiler would do is look at x and say, you know what, an integer takes up 4 bytes on this particular system, so the next integer would be here. Essentially it assumes that when we add 1 to a pointer, we're trying to point to the next logical int. If we do the same thing with a double, right, so here x is, and a double takes up 8 bytes. So if I start with address 104, we'll just assume that this is the address where x starts, and I go add 1 to my pointer again. Well, now I'd go up to the pointer would change to 112. We start at 104. 8 bytes are taken up by this double, so the next logical double would start right here and take up the next 8 bytes. Behind the scenes, this is exactly how arrays work. Right? We've been exposed to this idea that arrays consists of a base address, and then this index is an offset from there. Right? So if I declare an array quiz of size 3, what I really get is 3 consecutive integers in memory. And quiz itself, if I just use the word quiz, would correspond to the address where the first element is located, that base address. As soon as I go index into an array, I say, like, give me quiz sub 2. Well, the compiler interprets that as start from quiz and add 2 ints. Do that pointer arithmetic. 2 ints in this case would be 8 bytes, so we start at address 100, add 8, we get address 108, and that allows me to instantly jump to the right location in memory. Right? I don't have to walk there. I can calculate exactly where we need to be. This is all kind of interesting and useful stuff to know, but the real important point is arrays and pointers are very closely related. Right? An array is a base address of a contiguous chunk of memory. A pointer is a memory address for one particular type of data. So all that's different is the array has this notion of elements, of multiple elements, but we can simulate that with pointers by just adding to the pointer. You can go back and forth. Because these ideas are so closely related, you are absolutely free to take something that you declare as an array, so nums here is an array of size 3, and treat it like a pointer. So if I ask for nums, I'm getting the memory address of this array, and if I dereference that, well, that's giving me the first element, 5. If I add 1 to nums, I'm doing pointer arithmetic, so I'm getting the second int within nums, and I dereference that, and I get the second int in the array. And if I add 2, I'm jumping from the base address 2 elements in, and I get the 7. This would be a bizarre thing to do intentionally, but we can take an array and treat it like a pointer. We can also turn around and do the opposite. I can have a pointer, so get x's address, right, and x is 5, store that in this pointer p, and ask for p sub 0, which sub 0 says don't add anything to the base address, just go to this address, pretend it's an array, and get me the thing that's right there. Well, the thing that's right there is 5, right, what x is. Now, I'm absolutely free to go say, well, give me the second thing, p sub 1. And so it's going to go grab whatever's in memory right after x, and in this case it happened to be kind of gibberish. This does not make sense logically to go access that element, we know that, but the compiler, once we start treating something as a pointer, we're free to index into it, and maybe we know better, right? And this is exactly the trick that we use when we do dynamic allocation. We ask for an array to be created on the heap, we get back a chunk of memory, and all we get back is the address of the starting thing. And so then it's up to us to index into that memory as if it was an array and make sure we don't go too far. So basically, anywhere you need an array, you could use a pointer instead. All right, if I've got a function that takes in an array called nums, an array of ints, I could instead just pass in a pointer, but then go ahead and write the body of the function exactly the same. And that's one of the reasons you may have seen an error like this. I've got this fake function do stuff that takes in an int array called x, and I try and pass it a single int. All right, I'm messing up here. I'm not passing it an array. I'm passing it a single int value, and I get this error, invalid conversion from int to int pointer. Well, there's no int pointer involved here, but really that's how the compiler's interpreting this array is, oh, well, that's an address, memory address for an int, right? The address where this array starts. Well, an address for an int is an int pointer. So that's kind of the deeper story behind some of the weird compiler messages you may encounter. We can't normally return an array from a function. So if I've got a function foo, there's absolutely no way to write something that's going to compile that would look like this. Foo returns an array of ints. You just cannot do it in C++. But what you can do is return a pointer. All right, so I can have a function foo that promises to return the address of an integer, a pointer to an integer. And so I could then make an array out on the heap, so a new int of size 10, store that memory address, right? I ask the operating system to allocate the memory. I store the address in x, which is a pointer to an integer, and I return that, which is the right type. I promised to return the address of an integer. That's what I did. But I just happen to know that the address I'm passing back is actually the start of a block of 10 integers. And so then we could go ahead and use that as an array. We could use that idea to craft a function like this. This first n even numbers. So I can pass in a number n, say give me the first 100 even numbers. And it's going to construct an array for us with 2, 4, 6, 8, 10, etc. Well, we can't return an array, so we have to return it as a pointer. And because we don't know until we get to the point where we're running this code exactly how big the array is, we have to create this array out on the heap. We also have to have it out on the heap so that when we return from this function, it doesn't get destroyed. So we do something like allocate a new array of ints of size n. We get back the memory address, and I store that as numList. I get back a memory address from new, and that's why it stores a pointer to an int. But that pointer I can just use as an array. I know that it points to this whole array of ints. And so I can happily walk through that, up to size n, and fill it with values, and then return that pointer. So what that would get used like back in main might do something like this, called get me the first n even numbers, and pass it 30. We know we're going to get back an array of size 30, but it's going to come back as a pointer to an int. And so I'd store that as nums, and then I can turn around and start using that just like an array. I can index into that pointer just like it was an array, because I happen to know that that's what it's really pointing to. And so I could count up to 30. Now, since this function called new to allocate space on the heap, and it does not delete it, which is good because we want to get that memory back out of the function, it does mean that my main now would be responsible, once I'm completely done doing the work, for deleting that array, or I would have a memory leak.